Okay, so hello everyone. I want to speak today about very interesting geometrical structures which called fractals. So what is the fractal? We have several definitions. One of the definition is geometrical self-similar form. It is not good definition because we don't know what is the self-similar, and it is appears that many of fractals are not self-similar, which means the smaller, if you enlarge the scale, you don't see the same structures, but similar. So self-similar form, it is something not rigorous. Second definition is fractal is geometric form with fractal dimensionality. Rodrigo.
Adi,
Yes.
are you sharing your screen?
Yeah, are you sharing anything?
This is the problem. Sorry for that. Now.
Okay. Thank you.
So this is the first slide. So the second definition, fractal is geometrical form with fractal dimensionality. It is the mathematical definition. The problem, not so many people knows what is the fractional or fractal dimensionality. Third definition says geometrical structure containing detailed structure in arbitrary small scales. What it means, it means something that you see in the right picture. You go in the scale, you enlarge the scale of the picture, and you see that you have no straight lines. Let's go to the history of fractals. So something about fractal structure we can meet at the ancient Greeks. I'm not going to ancient Greeks. I want to go to 19th century, where we reinvented the mathematics. And when we reinvented the mathematics, we extended the mentions or definitions of well-known measures. So one of the measures we used is the length, and we extended length to something which calls norm. It's a function with the these three axioms. The distance we extended to metric. It is some function with their axioms, and the volume we extended to a function which calls measure. And when we extend, and in 19th century, we started to deal with infinities, infinity large and infinity small objects. And the mathematicians of 19th century started to find paradoxes, or so-called paradoxes, something which is right but counterintuitive. For example, do we have some structure with infinite number of points, but it is empty? Or do we have something with finite area but infinite perimeter? Or can some shape be not dense? Or if you know Banach-Tarski paradox, can we take the sphere and split it to finite number of particles, and then from these particles construct two equal spheres? This paradox is related to something that till now we're arguing. If there are objects in real life that have zero volume or zero space or zero length. And now I want to jump to 20th century in 1951, and it was the start of the modern history of the fractals. It was the Lewis Richardson. He was geographic worker. He noticed that Portuguese reported the measure of border of Spain with the Portugal to be 987 kilometers, but Spanish from other side reported that their border is 1,214 kilometers. And this led to some paradox, which called the Richardson effects. What was the measuring techniques? They go to the plane, they filmed or photoed from the plane the coast, and then on the map they take some standard ruler with length L, and they covered the border with the standard ruler. And it appears that if you have, let's look here. If you take the bigger ruler, so you see you have only two measurement units here. But if you take smaller ruler, you have 1, 2, 3, 4 or 5 units. And it appears that the length of some object or length of coastline depends on the length of the ruler. And it appears that some geometrical forms have the maximal roughness or minimal roughness. You decrease the length of the ruler till some minimal object, and then no matter how you decrease this ruler, the perimeter remains the same. But there are objects that you can decrease the length of ruler as small as you want, and the perimeter will extend. And in some cases, you will reach the infinite perimeter. And this effect was explained in the book, which called "How Long is the Coast of the Britain" by Benoit Mandelbrot, where he discussed such structures with infinity roughness or infinite self-similarity. He didn't call it fractals. He coined this word a little bit later, but it was the first book on the fractals. But Mandelbrot was the first which officially said the word the fractals and started to investigate. He created a couple of mathematical fields, and one of the fields was fractal geometry. But we can jump to the 19th century to a mathematician called Georg Cantor. He is very related to our team because he was born in Russia, and he grows in France, and he was of Jewish and Danish origin. In 1983, he created the next set, which called Cantor set. How we build this set? We take the interval from 0 to 1, split it on the 3 parts, and then we exclude the open middle part, 1/3 and 2/3. Then in next iteration, the remaining intervals we split on 3 parts and remove open intervals, and we continue to do this infinitely. And K infinite is our Cantor set. It is very interesting set. And the first question, is this set empty? Can you guess if it is empty or not? It is not empty. Obviously, if you take open interval, so end of these intervals are remaining in the set. And when you once, yes, Amino.
Yeah, sorry, maybe we jumped a little bit, but I didn't really understand what the Cantor set is relevant for. Like, what are we measuring with the Cantor set, basically?
Not measuring. It is Cantor set. It is geographical structure. Later, I will say that it is the first ever mathematical example of fractal. In 19th century, they didn't know that it is fractal, but this is the first fractal in the history of mathematics. Spoiler, yes. So first of all, you have many points with infinite many intervals between them, because you infinitely reduce the intervals from the Cantor set. But Cantor set has at least ends of intervals, so it is not empty. But what is the length of this set? We can measure the length of excluded intervals. So we remove from the 0.1 interval 1/3, and then 2 times 2 9s, and 4 27s, and so on. And it appears to be geometrical progression. So length of all excluded interval is 1. So we have not empty set. We have points in the set, but the length of this all this set is 0. But how many points in Cantor set? We can mark left interval by L, right interval by R. Next iteration, we can mark 0 as LL, the 1/9 as LR, and RL, RR, and continue till Ensof. And when we mark each point in such manner, we have 0 is infinite number of L's, L, 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 L. Rightmost number 1 is R, 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 and 1/3 it is left interval and rightmost interval. So it is L, R, 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 R. 2 9s is, we are going to L, we're going to R, and going to L, and continue with L. So each one of the points of Cantor set we can encode as infinite series of L's and R's, or if it is 1 or 0, we can encode it with infinite binary numbers. And it said that Cantor set is uncountable, or the cardinality of Cantor set is cardinality of continuum. And what is said, the meaning of this, that number of points in interval 0, 1 is continuum, and number of points of Cantor set is continuum. So we exclude infinite number of points from the Cantor set, and still the number of remaining points remain the same as in interval 0, 1. Now, what is the dimension of Cantor set? And here, this is the mathematical proof. What is the fractal dimensionality, or what is a dimension of fractals? What is dimension? One of the definition of dimension is factor how we enlarge the geometrical structure. For example, we have some unit of measurement of length L, and we extended it 3 times. And in the geometrical figure, you have 3 unit intervals. So 3 increased to 3 in degree 1. And we say that this degree is dimension. If we take this structure and enlarge it 3 times, we have 9 segments, or in 3 in power of 2. So it is 2-dimensional figure, and this is 3-dimensional figure, because when we enlarge in 3 some structure, we have enlarged in degree of 3 points of measure. And in common, this is the formula, or dimension is how many points of measure we receive when we enlarge some structure by epsilon. This is the definition of dimension. And what is the dimension of Cantor set? We take the interval 0 to 1 and increase it 3 times. So we have interval from 0 to 3. And you can look that already second iteration gives us exactly the Cantor set. Set from 0 to 1 with excluded middle part till Ensof. So when we increase the original Cantor set by 3, we increased all the structure by 2. So dimension of Cantor set is 0.631. And this is the definition or proof that this is the fractal. So till now, we dealt with the regular geometrical structure, and we know what is a 1 dimension, 2 dimension, 3 dimension, and it appears that we have fractal dimension. What is the interior of Cantor set? So interior point is the point if you can take arbitrary small ball around this point, you will see only points of set in this ball, no matter how small or big this point, this radius. In Cantor set, no matter how infinitely small ball you take, you will see that near each one of the points of set, you have infinite number of points of not in set. It means that in the Cantor set, no interior points. It is totally disconnected. So summary, Cantor set is the fractal with infinite number of points. And unless there are infinite number of points, unless we throw from 0, 1 infinite number of points, Cantor set has exactly the same number of points as in line in interval 0, 1. And Cantor set has no interior points. His length 0 and dimension is less than 1. It is very, very strange set. And from this set in 20th century, we have a family of interesting creatures which are extension of this set. Let's go to extension of Cantor set, which calls Sierpiński triangle. Wacław Sierpiński was Polish mathematician of start of 20th century. And how we build this fractal, we take the triangle, we remove from the triangle the middle triangle, and we have 3 smaller triangles, and then we continue infinitely. And we receive this object. This object, as extension of Cantor set, it is not empty. It contains infinitely many number of points, but it has no interior points, and his area is 0. And his dimension is not 2, but 1.6. What is interesting with the Sierpiński triangle, that iteration n of building of Sierpiński triangle has the relation of Hanoi Tower game. So I think, I hope you are familiar with Hanoi Towers. You have a game with 3 rods and number of discs with different diameters. And the game, you must move all these discs to other rod by respecting only 2 rules. Each time you can take only 1 disc, the upper disc, and no disc may be placed on top of disc which is smaller. So this is the right move, but if you switch bigger disc and smaller disc, it is not right move. So how Sierpinski triangle connected to Honai Tower. Let's look on the game with only one disk, and we can create a moves graph, or we call it Cayley graph. So you start with the disk on the rod A, and you have two possible moves. Or you go to B, or you go to C. And this is the solution, because one disk game, you finished it. If you take two disk games, you can use the fact that we already have solution of the one disk game. So when you solve the one disk, let's go here or let's go here, you have two remaining games with one disk that their solution you already know. So you need only to solve the first triangle, and no matter where you solve it, to left or to right, you have some problem which is already known. And for n disk game, we have recursively we can recursively solve this game by solving n-1 disk problem and then solve the remaining disk. So this is the Sierpinski triangle of size n. Another extension of Cantor set called Sierpinski carpet or Sierpinski gasket. It has infinitely many points, as many points as in interval 0.1. It has no interior points, and his area is 0, and dimension is 1.9. What is interesting with this fractal, that it is used for antennas. Why? I'm not came from the physics, but it is known that if I want to listen for some frequency, my antenna must be of size of this frequency or multiplication of the size of antenna. As a result, we can see many antennas of many size because you want to listen or to see different frequencies. But in the fractal we cannot build in the real life. Fractal, we take Sierpinski carpet of n iteration, n first iteration. You have different lengths between empty parts of the carpet. So you can, in one antenna, you can listen several different frequencies. It is very easy to fabricate because it is a recursive structure. Easy just to create CNC program or just program it. And the fact that if you take some geometrical structure of same sizes, his dimension will be 2. And the fact that dimension of Sierpinski carpet is less than 2 says that it is you need less material to produce it, and it is more lightweighted and more easy to save money and to save material. Another interesting extension of Cantor set is a 3D structure, or it looks like 3D structure. It is a Sierpinski tetrahedron. You build it as Sierpinski triangle, but with pyramid. So you take pyramid, you take the middle part of pyramid, and you receive another pyramids, and you continue to go. What is interesting with a Sierpinski tetrahedron, that unless it looks like 3D structure, his dimension is 2. And it is easy to look it in one of the projection that his projection is just square. Another interesting extraction is called Menger sponge square pants or Sierpinski cube. It has no interior points, is area 0, and his dimension less than 3. Now I want to go to another family of fractals, not as the yes, it lives under the sea. Yeah. And next interesting fractal called Koch snowflake. Koch was a German mathematician, start of the 20th century. How we build? We start from triangle, but we extend it. We create another triangle here, and we remove the inner parts, and then continue, and we have a shape of a snowflake. What is interesting in this fractal? First of all, his area is limited. You can bound it by hexagon or just circle. You can bound it by circle, and this is the limit of this area. A0 is the original triangle. But what is the perimeter of this Koch snowflake? The perimeter, it is not rigorous proof, but intuition. We take something of 3 parts, the size of the triangle, and we create from this 4 parts. So the perimeter of snowflake is the area of original triangle extended each time, and each edge extended by 4 thirds. The perimeter of Koch snowflake is infinite. So we have something, we have a geometrical structure which is finite or with finite area but infinite perimeter. And what is dimension of Koch snowflake? It is 1.26, and we have already intuition why. When we enlarge something by 3, we have 4 elements. So his dimension is more than 1. And I remind you that it is line. So line, we say dimension of line is 1. No. Here, example of the line, which dimension is more than 1. And another interesting feature or ability of this line, that it is impossible to draw tangent line to any point, or this curve not differentiable in any point. And now I want to go to another example of interesting fractals. I already said that we have a line, and line we intuitively think that line is of dimension 1. But here Koch snowflake of dimension more than 1. So maybe we have lines with dimension more significantly more than line. Or in another question, Koch curve or Koch snowflake cannot fill all the space. His area is limited. But maybe we can build curve which is not self-crossing and visit all the points in the plane. And welcome to Peano curve, Giuseppe Peano, Italian mathematician of 19th century. And we're starting from some square, we divide it to 9 subsquares, and we just visited them. Just think that this line is of the size of this subsquare. So we visit all the points of the line. Now each one of the subsquare we divide on the 9 subsquares, and we continue the line by flipping or rotating this pattern, piano curve. So we fill this in this manner, and then each one of the subsquares you divide, and you continue infinitely. And you receive, first of all, a line which not crossing itself in any point. It visits any point only once, but it fills all the space. So cardinality of the curve, number of points on the curve is the cardinality of continuum. Infinitely many points. His dimension is 2. His dimension is 2. It is. It says that it visits each point of the plane, and it is not differentiable in any point. Another extension of a space filling curve called Hilbert curve by David Hilbert. He was a German mathematician, very famous. And fun fact that when the Nazis came to rule in the Germany, they almost dropped it to the prison and to the concentration camp because his name David. He was pure German, purest German, as you can see, and finally he was very famous man. So finally someone said them, it is a very famous and greatest scientist of Germany. You need to respect him. And till the end of the war, he was in his home, not attending and not participating in any Nazist, in any war, in any Nazist activities. But it is fun fact because his name David, they killed him. So Hilbert curve is the same curve, but splitting not in 9, but 4 subsquares. So you have only 1, 2, 3, 4, and you continue. Cardinality of the curve still continuum. Dimension is 2. It visits each point of the plane. Length is infinite, not differentiable in any point. And these curves, Peano curve and Hilbert curve, have a very interesting property called locality preservation. When you take the memory is straight line, and you fill the memory with some addresses, points of this straight line, and then you fold this straight line into the 2D space, you see that 2 consecutive points of this line are 2 consecutive points on the memory. And this this locality very useful by building caches. You have a small number of cache misses, and it is used in Google Maps. For example, when you scroll Google Map to enlarge some region, so they take the part of the map and insert it into the cache, and all the points of this map with a high probability are in this cache because it is preserved geometrical locality. Another example is IP addresses management in picture detections. It is highly used in the computer vision. Another very, very interesting object, which was not, no one thought about this object, that it is fractal. It is random walk or Brownian motion. What is Brownian motion? You have a particle, and each period of time you move randomly to some direction. And what is the randomly? You have normal distribution, which called white noise, his mean is 0. You do not prefer any of axes to go, but you coin the next movement from some Gaussian noise, from some distribution with variance u. And it is appear that this process, which called Wiener process, by Norbert Wiener, one of the famous in computer science peoples, it appears several interesting properties. One of the properties that it is self-similar. If you enlarge scale of some random walk, you will see the same process with same probabilities, with same mean, and with same variance. And the dimension of this random walk appears to be 2. The random walk visits all possible values of the space, which leads to something which is known gambler's ruin. What is gambler's ruin? It is appears the stock exchange prices may be modeled as random walk process, as a Wiener process. And you start from some maybe very high point, and you start with maybe very high probability to win. But if it is random walk, it must visit all the points of the plane. So sometimes it must go to 0 and cross the 0. And when you cross the 0, it means your assets are 0. You lost all your money. More than that, it visits 0 infinitely many times. So in pure modeling, if you play with the stock exchange, more time you spend on the stock, more probability you lose your money. So it is some phenomena which called gambler's ruin. Another property of random walk another property of random walk in 2 dimensions, that with probability we can say 1. The definition is the probability arbitrary close to 1, as for almost sure 1. If you start from some starting point, you will visit this point in some time. And when you start Brownian or random walk, it is always create clusters, or it's called Brownian islands. Each and every time they started to simulate this process, they received the same the same outcome. The islands are different, the shape are different, but it is always close structure, and always his dimension was 1.33. And this is fractals. More than that, these islands are very, very, very similar to real world objects. And if you take the same Wiener process with some extension, you have parameter called Horst exponent. And this Horst exponent is responsible to create more rough. It is roughness measure. It creates more rough or more smooth curves. So by varying this exponent, you can create islands with arbitrary coastline dimension. And this is the left island with the created by Wiener process. And it has the same dimension, 1.25, as Great Britain. And moreover, they do many experiments, and they find Brownian islands with the same dimension as real islands. And this gives possibility to create islands and objects very similar to or equal to those objects that we have in the nature. For example, terrain. All these terrains are created by a recursive process, by a fractal process, and you just need to adjust only the roughness coefficient to have more rough or more smooth terrains or objects. For now, I want to ask, is the fractal is something from real life, or maybe fractals it's something which is just mathematical object? And I want to cite and continue with the creator of this geometry, Benoit Mandelbrot, that he said that when he think about it, we almost have no smooth object in our nature. Almost you cannot see almost nowhere round object or plane object. All objects are rough, and moreover, if you start to look around, you see that fractals are everywhere, and our world built from fractals, starting from clouds and atmospheric sorry, atmospheric artifact like lightnings till human body and till real objects and universe clusters are fractal, and they have fractal dimensionality. So this is the example of real life fractal broccoli of dimension 2.8. We have surface of lungs. A surface of lungs is 2D object, or I want to say 2D object. It has has no volume, but his dimension is 2.97. It is almost 3. So it is 2D object, but it acts as 3D object. And this is why it is very compact, but it gives us 6 liters of air capacity and 85 square meters of surface. Very light, very compact, but surface and ability very, very big. We have rivers which are fractal with fractal structure. We have trees with the fractal structure. And we can continue, lightnings, clouds, human body, blood cells. Almost all objects around us are fractals. And we have 10 minutes more. I want to present the creator of the fractal geometry. It is also very related to our team because his origin is Lithuanian Jew. My wife Lithuanian, so I'm also related to it. He is born in Warsaw. He grown in France, and after World War in France, he received his education, and he moved to America after World War II, and he was famous in America. He was IBM fellow for many years, and interesting, he was a nephew of Bourbaki. If you know, it was an interesting group of French mathematicians which presented papers by name Nicolas Bourbaki, and long time no one know who is this man Nicolas Bourbaki. And he was very versatile person. He wrote and investigated many areas of interest, and he created a couple of fields. And I want to finish with a question. So his name is Benoit B. Mandelbrot. And what is the B stands for in the name of Benoit Bill Mandelbrot? So it is joke. B in the name of Benoit B. Mandelbrot stands for Benoit B. Mandelbrot. So I finished. Thank you very much. And if you have something to add, please add. If no, we are finished. And
Okay, thank you, Vladi.
Thank you very much, Vladi.
hi.
Thanks, Vladi. Great presentation.